Hi everyone, I'm Jianwei Yang. Today I will present our work on foot-eye plotting, design and evaluation of foot-eye teleportation techniques in virtual reality. Teleportation is widely used in VR because it's simple and helps reduce motion sickness, so it's a great default, but it has a bottleneck. Most teleportation is hand-controlled, but it breaks down when users need both hands for tasks. That creates interference between moving and doing. In training, logistics, or FPS games, hands are constantly busy, so hand-based locomotion becomes disruptive. So we need a hands-free alternative. Hands-free locomotion can reduce this interference and improve performance in multitasking. That motivates our direction. Beyond the performance, hands-free teleportation can feel more immersive because hands stay on the primary task. Now the question is, what modalities should we use? Gaze is fast and precise for target selecting, but using gaze to also confirm causes the Midas touch problem. Feet offer embodied and stable gestures, but feet are less precise for aiming. So we asked, instead of forcing one modality to do everything, can we combine eyes and feet in a more natural way? In real walking, eyes choose the destination and feet execute the action. This coordination is natural. That inspires our foot-eye teleportation design. Foot-eye coordination works well in hands-free test input, but it is still underexplored for VR teleportation. So our work fills this gap. Next, I will show our design framework. All our techniques follow two phases: targeting the destination, then activating the teleport. This structure lets us systematically test different combinations of targeting and activation. And to guide the design, we formulated three key design considerations. First, prevent accidental triggers. Second, decouple locomotion from looking around. Third, stable and ergonomic activation. With this, we designed four techniques. ETAP and EMIP both use gaze for targeting. You look at the ground where you want to land, using binocular average gaze for stability. Then we use foot actions for activation. ETAP is a single 4-foot tap. EMIP is a small in-place step. FFW used the right foot 4-foot pin for targeting. Rotate the right foot to set the direction, and lift height controls distance along the beam. Activation is a voluntary eye wink, avoiding head motion. IFD use 2-foot targeting. Direction comes from right foot orientation. Distance from interface distance. Wider stance means farther. Activation is 0.5 second gaze stare on the beam, designed to be stable and intentional. Our baseline is FFN, adapted from the best performing technique in the most related teleportation work, for the beam aiming for targeting, with a head nod to activate. We use the focus vision eye tracking for gaze, wink, and dare, and Vive ultimate trackers for foot motion with calibration and smoothing. Next, I'll show a short video demonstrating how the techniques look in practice. Okay, let's move to the user study. We ran a lab study with 20 participants. We compared 5 techniques across 3 distances, measuring time, teleports, offset, plus NASA TLS, SUS, and a custom scale. We used a simple thing with clear targets to keep the evaluation focused on interaction, not visuals. Participants teleported to targets at 2, 6, 10 meters, within plus or minus 6 degrees, totaling 180 trials per person with counterbalancing. Now the results. First, efficiency. Technique significantly affected time. ETAP and EMIP were consistently fastest. FFN was slowest. Efficiency is not only time, another indicator is how many teleports users need. FFN required the most teleports, meaning more corrections and lower efficiency. Next, the offset. Interestingly, we observed no significant effect of technique on spatial accuracy at all distances, so all 5 techniques offered the comparable precision. Now let's look at how participants fared, starting with workload. FFN had the highest workload, ETAP and EMIP were lowest, with FFW and IFD in between. Workload is one part of experience, usability is another. SLS scores favored ETAP highest, then EMIP. FFN was much lower. We also asked the participants directly about convenience and confidence. Participants felt more confident and convenient with ETAP, and least with FFN. Finally, overall preference. Preference strongly favored ETAP and EMIP, and consistently ranked FFN last. Now I'll summarize why these results happened and what design insights we can take away. ETAP and EMIP performed best because they align with natural locomotion. Also, replacing nodes with eye triggers like wink or dare helped eliminate instability and coordination issues. That's why FFW and IFD improved compared to the baseline FFN. Distance also influenced user strategies. At both short and long distance, gaze-based methods, ETAP and EMIP, were the most efficient because gaze targeting stays fast and precise. Foot-based targeting methods struggled more at long distance due to balance demands, and FFN was further hurt by node-induced jitter. IFD offered a stable compromise, but it required extra repositioning because users had to widen their stance to reach farther targets. Our procession was comparable across techniques. Confidence and perceived stability differed a lot. FFN was rated lowest, mainly because it felt unstable, while the decoupled and stable methods ETAP, EMIP, FFW, and IFD felt more controllable and reliable. So effective techniques must balance stability, error tolerance, and low learning effort to improve confidence and usability. Based on these findings, we propose several design recommendations. We summarize the key recommendations as follows. First, decouple modality loads. Second, use gaze plus a deliberate foot action to avoid Midas touch. Third, replace node activation with eye-based triggers. Fourth, leverage foot-eye coordination as an intuitive interaction metaphor. Fifth, consider context-aware design. Finally, focus on hardware comfort and compatibility. Our study also has limitations, which point to future work. Since our study was run in a controlled lab, ecological validity is limited. We also focused on discrete teleportation with a relatively small homogeneous sample, and our overlapping inputs constrained fine-grained analysis. Next, we'll validate in more realistic VR tasks, explore continuous or hybrid gaze-foot locomotion, recruit more diverse participants, and use higher resolution logic. Thank you for your attention.